Okay, let's get started. So first off, just want to say hello to everyone, and thanks for joining our webinar on Amazon Redshift Best Practices. My name is Rob Coster, and I'm an account executive here at Matillion, and will be your host for today. I'm also joined by my colleagues and main presenters, Dave Langton, who is our product manager for Matillion ETL, and Kalyan Aranyan, who is one of our fantastic solution architects. What we are planning to cover today is discussion topics around best use of Redshift and how to enhance performance and features for this cloud data warehouse platform. The reason we feel we are best situated to provide this webinar is that we deliver a tool called Matillion ETL. This tool is specifically designed to help you and your teams deliver and build out a data warehouse on Redshift quickly and efficiently. The tool has two main components, the first being the orchestration of data into Redshift, and the second being the transformation of data within the Redshift data warehouse. The agenda for today is I'm going to quickly run through two slides of Matillion ETL, and then we'll pass on to my colleagues for discussion topics on Redshift. Towards the end of the call, we will leave plenty of time for Q&A, with the goal being to answer any specific questions you have that pertain to your specific use case and or just a general understanding of Redshift. Just some general housekeeping here. The Q&A panel will be going live later, but I do believe you can stage your questions immediately, and after the presentation, we will dive into them. So on the first slide here, I'm just going to run through what Matillion ETL for Amazon Redshift is. So we're a data integration tool built specifically for AWS and Amazon Redshift. We provide a push-down ELT architecture through an intuitive browser-based UX and UI. We have a very powerful feature set, and we can be purchased. It's a retail-like acquisition through the AWS marketplace. We're going to go on to slide 2 here now. And here we go into some of the benefits and highlight the key points that I just made on the last slide. As you can see, ELT architecture. With that, we flip the script on traditional ETL processes. With traditional ETL tools, as I'm sure many of you know, data is taken out of the database and then put into a dedicated infrastructure to be transformed, which is where actually a lot of our customers have told us they run into many bottlenecks, particularly around scalability and performance. After waiting hours and sometimes days, the data is then loaded into a data warehouse. With our push-down ELT approach, we change the order of events and allow Redshift to do all of the heavy lifting, specifically utilizing the power of the Redshift cluster. So all of the transformations are processed within the database. Second point here, we have an intuitive UI and UX. The tool is accessed through a browser, which gives you the ability to visualize and validate components in real time against the cluster, vastly improving error handling. I would also like to add that to this, the low barrier of entry for use of the tool. I think having the ability to visualize the orchestrations and transformations and have them run on their own eliminates the need to have highly specialized technical skills, which allows not only technical users to benefit from our tool, but also non-technical business end users as well. The third point we'd like to make is our tool is built specifically for AWS. So we are proud to be an advanced technology partner on the Amazon Partner Network, as well as we are only one of about 20 big data competency partners, which means in addition to Redshift, we integrate seamlessly within the Amazon Web Services environment with components such as S3 and CloudWatch. The last benefit we want to discuss is our retail-like purchasing method. Our tool is accessed through the AWS marketplace, and you can be up and running in 5 minutes or less with our cheap utility-based pricing model. We provide a 14-day free trial, which we fully support with our team of solution architects, and we do this to prove out your specific use case and make sure that Matillion ETL is indeed the right tool for you. If we go on to the next slide, I'm just going to share some information on some of our customers. So as you can see, we work with a wide range of companies, ranging from startups who are born in the cloud all the way to Fortune 100 companies such as GE. If you'd like to learn more, please reach out to us at matillion.com. We'd be more than happy to provide some additional information, share some use cases with some of our customers, or set you up on a call with one of our solution architects to discuss your specific use case or any questions that you have. So without further ado, I'm going to pass the baton over to my colleague Dave to run you through some Redshift best practices.
Great, thanks a lot for that introduction. That was a fantastic introduction. What I'm going to do now is just run through the agenda for the rest of this webinar. If you're going to do something real and have a use case with Redshift, then these are the things you need to think about. These are what you've got to do. You've got to design a schema, you've got to load some data into it, and then you've got to query that data. And it turns out that in terms of best practices, the most important things are this order as well. So the biggest wins are in schema design, followed by the loading. And then if you get that right, querying becomes really easy. So let's dive straight into some schema design. This part of the presentation isn't relying on the Matillion tool. This is pure Redshift, but what we will see is a little bit of a demo later on, which does show how this can be used within our tool. So with schema design, the first thing you need to understand is how Redshift architecture pushes data around lots of different nodes in a cluster. So you'll typically only deal with the Redshift leader node, and your client applications, whatever they may be, will see that as one database. Whereas in fact, the leader node is a front for lots of, or potentially lots of compute nodes. And you can run a single compute node, or you can run dozens of them. And within each compute node, they're further subdivided into slices, and your actual business data sits in the slices. And in order to perform a query, all of that data gets fed through the leader node and back to the client application. So when I say the data gets distributed in these slices and in these nodes, what does that actually mean? Well, every time you create a table in Redshift, you give it a distribution style. And if you don't give it one, you get a default, and the default is even. But if you do choose one, you've got three options: all, even, or key. Now, if you choose all, it means that every single compute node has a full copy of that table. And actually, you get copies of the same data on each node. That's actually quite a good thing for small tables, because when they're involved in joins, the rows don't ever need to be sent to another compute node over the network, because there's a copy of them on every compute node anyway. But of course, if you make all of your tables distributed then you're just putting a copy of the whole data warehouse on every compute node, and you'll run out of space. So it's great for small tables, lookups, dimensions, but less so for larger tables. But they can never be skewed, because that's not really a relevant concept, and they're never redistributed at runtime, so they're nice and fast. The default one, even, that's great for fact tables with lots of small dimensions, because you don't need to worry about how the data is distributed around the cluster. It will just be evenly distributed, more or less at random. So again, you won't get any data skew. You won't get skew is when lots of rows sit on one node and all the others are empty, which is generally a bad thing that you want to avoid. So even takes care of that and just makes sure it's nicely distributed. So key is the hardest to get right and the hardest to configure. And in a few minutes we'll look at some examples so you know when you've got that right. But it's great when you've got very large tables. When your tables are really large, you need to join them together. The worst thing is if the rows that need to be joined are on different compute nodes, because you saturate the network and it really becomes a barrier to that join happening quickly. So what happens there is, as the data flows through the leader node, the key that you have to choose in your data set is hashed, and based on the hash, it dictates where that row will sit in the cluster. Now, if you make a poor choice of key, then you get skew, and you can end up with a lot of data very unbalanced, which is not a good thing. The reason you'd use this is to avoid all of that expensive redistribution at query time. So dimension keys and join keys are typically what you'll want to use key-based distribution on, but only when the table is so large that all is not an option, and where you know that it's important to match on the keys and even isn't really performing for you. So as I say, we're going to see some examples of that, and it is easier to see once you get some query plans up. But for now, I'll just skip and talk about some sort keys, which are the next slide. It's a related concept, and the examples cover both of these things. Now, typically in a database, you don't care how the sort order is on disk. You care about sort order when you run a query, perhaps, and that's what order by's for, but the physical storage is not really of concern. But on Redshift, with its columnar architecture, it is important at query time that the optimizer can make decisions based on the physical sort order. And it's used in a number of optimizations that would usually be left to indexing in traditional databases. But there are no indexes here, so this kind of does the same job or a similar job. It's used to optimize filters. It's also used to optimize joins because it can use a merge sort rather than any kind of hash join or hash tables. It will slow down loading the data into the cluster. That's just because there's an extra step to sort it, but that should get paid back at query time. Now, every time you do an append into a table with a sort key defined, and the data is sorted, but only for that load. So if you constantly append new data onto the end of a table, what you get is these unsorted regions, which are sorted in themselves, but just tacked on to the bottom of the file, which isn't a big problem if you're doing it infrequently, but over the time, it ruins the benefit of actually defining a sort key in the first place. And a vacuum is the operation that will resort all those unsorted regions back into a nice, efficient table. When you're defining a sort key, you can choose between compound sort keys and interleave sort keys. Now, the compound sort keys optimize things on their leading columns. So if you sort by A, B, and C, it can optimize queries involving A or A and B or A, B, and C, but can't optimize things on just B or just C. Whereas the interleave sort keys aren't quite as efficient overall, but they can use any combination of any of their keys, and you can have up to 8 columns defined in a single sort key. So they're more overhead, but much more flexible. Now, the diagrams on the bottom right show the data storage for the compound sort key versus the interleave sort key. And you can see that the compound sort key works as you would expect it to. All the values are sorted by the first part of the key and then the second part. But on the second one, you can see that actually they're kind of half sorted into blocks that alternate. And the example underneath shows for different filters how many blocks need to be read. And you can see a clear trade-off that the compound sort key can do better in some cases, but can also do worse, whereas the interleave sort keys provide a benefit with both filters, but it's not quite as good in the best case. And the best thing to do really there is to experiment. Now that's quite a lot of slides, quite a lot of dense information, and I think at this point we'll switch over to Kalyan, and he'll show you some of these concepts on real tables and what that actually means to the query plan, which is the tool you can use to know whether you've got all this right or not. Over to you, Kalyan.
Thank you very much, Dave. And okay, good. So hello, everyone. I'm going to walk you through a few examples that demonstrate how distribution or having various styles of distribution or even sort keys can improve your query performance and things as such. Now, best practices demos generally tend to be pretty dry in that they're quite theoretical. In this instance, we just thought we'd come up with something so that you can see for yourself as to how the different decisions we make in terms of distribution styles and allowing sort keys will allow us to run efficient queries. This is not generally something we perform on a regular product demo. If you're interested in knowing more about the product, you can obviously visit our YouTube channel. There are weekly demos that you can participate in, and there's various other ways you can get in touch with us. So as we go along, I'll first just talk about the type of data we're trying to work with over here. I'm working with a really large table. It's about flights that have occurred in the US a while ago, or a couple of years. I'm going to select one of those here. So the first example, which I've already labeled as bad, is basically two copies of the flight table who've been where the distribution style is even. And they're being joined on a specific key, which is the ID of these tables. Now, if you look at the sample tab for the flights table, you get a quick row count, and you can see it's got about 120 million rows there. And the other table as well is just a copy of it, so that's got a similar or equal number of rows. And when you look at the join here, so you can see we are performing a very straightforward join on the ID columns on these two tables. So, of course, we're not going to run this query right now. I ran it previously, and I already made a note of the time it takes, around 9 minutes or a bit more. But for now, we'll just use the query plan generated by Redshift to analyze how it affects the query performance. So let me click on Get Plan, basically get the query plan for this SQL that's generated from Redshift. And of course, you can see that the certain aspects of the query plan are highlighted in red, purely based on the fact that that's really not good when you want to perform a join as such. So the option returned to us is ds-dist both, which means for both tables on either side of the join, data may need to be redistributed across nodes in order for the individual nodes in the cluster to be able to compute a join. Again, if you look at the cost, of course, cost is just an indicative number in terms of, it's a relative number in terms of the processing power that may be utilized. And obviously, you can see that's a really large number at this point. To show you how we can improve on this, it's best if I was to move to the second example on your screen, which, of course, I've already labeled as good. The difference between these two is the flight table in this instance is distributed on a key. It's exactly the key which we're using in the join, which is the ID. Of course, I can't show you how that was created right away. But so in this instance, both these tables, it's still the same. They've still got about 120 million rows in them, but they're both distributed on a key, which is the ID I'm using for the join. So if I now select the join, go back to our Plan tab and click on Get Plan, you can see that it says ds-dist none. Of course, it's already in green, which means it's a good one to go with. And if you also look at the cost displayed here, the total cost, it's way lower than what it was on the other one. It's many magnitudes lower, in fact. And you can see just by making a small change in the by adding a distribution key, we're able to bring down the cost considerably. Moving on from there, there's a third example again, it uses the same two tables. But of course, here I'm pointing out it's going to be even better compared to the previous instance. In this case, the only change is that in addition to a distribution key, we've even added a sort key, and it's sorted on the ID field again. And it's the same for both these tables. Again, both of them have the same row count, and they're both joining on the ID column. And for this example, if I'm to click on Get Plan, you can see that it's now, again, it's still VS none, which means all data that's needed to perform the join is sitting in the respective nodes, and there's no data distribution necessary. And there's a really slight improvement in performance. Like previously, we had something around 2.25. But now we've got about 1.75 as an indicative cost of the operation. So whilst it's a small bump, but when you're dealing with large data sets, that can really make a lot of difference in terms of working with your data. Right. Moving on from here, we have two other examples. These two examples are again, the first one here is using the same flight table as in the previous example, and it's also implementing a distribution based on a key and is also being sorted on it. The difference between this example and the previous ones is that this example is more common in typical environments, in that the second table we are joining to is a much smaller table. So if I select my plane data, so the other table is essentially the information about planes that made these journeys as such. So if I get a row count, you can see it's about 5,000 rows odd, and you can even click on it to see what's really in there. So the difference between these two in this case is the raw plane info table, given that it's a small one. We've chosen distribution style to be all, in that it's held on all nodes. That is, a copy of the table is held on all nodes of this cluster, which means there's no redistribution required if and when we're performing join with between these two tables. So the only difference, again, sorry, I shouldn't say the only, another difference between these two scenarios, besides the size and the participating tables, is that the join expression has changed. So previously, we were performing a join between two tables which were similar or the same, essentially flights. But here, we're performing a join between flights and a planes table, and the join is now on the tail number column. So if I'm to select my join and switch to my plan tab, click on Get Plan, you can see it's all green. And of course, this time it's dsdist all none, in that it realizes that because the flights table is already distributed across nodes, there is no data transfer necessary, and the plane data is already distributed on a copy of the table is already present on all the nodes. So again, there's no data redistribution as such. Of course, you can see that the cost is different. Like in the previous query, the cost was down to about 1.75. But of course, I hope you appreciate that this query here is completely different, given the type of tables we're working with, and that it's not exactly distributed or sorted on the join condition, which is now based on the tail number. But still, given that it's green, I would just take a gamble and say that's still good. So how can we improve on this? So the last example we have here, we've already marked it as excellent. all it does is now it uses the tail number column for both the distribution key and is also used as a sort key for the flights table. And your raw plane info table, again, it still stays the same in that it's now able to, it's still distribution style is all as such on it. Now, if we go to our join, choose to do a get planned, you can see it's still in green, but of course, this is different now in that the previous one was DS dist all none, and this one is DS dist none, in that it already knows that both the participating tables are already distributed appropriately and also sorted to help with whatever it needs doing. So that's what that represents. And of course, when you notice the cost involved, this is again much lower. So the previous cost was somewhere around 63 point some number, but now it's down to 1.07, which is again a market difference between the two approaches as we see. So that's all from me for now. Back to you, David.
Thanks, Kellyanne. I noticed that one of the Q&A questions that's come in, rather than waiting for the end, I think I'll take it now because it's relevant to what you've just been talking about. And the question was really to define what redistribution is. So when you load data into the cluster and you choose a distribution key, that's your choice, and that happens at load time, and that's data distribution. Redistribution is what happens at query time if the choices you've made don't allow Redshift to satisfy the query without further moving the data around different nodes of the cluster. So it's just something at query time that's quite expensive and therefore a good thing to avoid, and these are tools that let you avoid that. So I hope that answers that question. So I'm just going to say a few more things about schema design before we move on to a new topic. These are all best practices that have really been, these have come out of delivering real projects for real customers. So if you took the best practices from Amazon, you'll notice there's a few that we don't mention, and it's because we've not really found them to be that useful in practice. But some of these ones definitely are. So use an appropriate type where possible. It's kind of obvious, but the problem with data warehousing is a lot of the data in its raw form is fairly unusable and needs a little bit of work doing to it before it would even pass as a date or a time or a number. So often you do have to just load things as text and deal with them as part of the ETL. But there's a rich array of functions that can clean up those strings and turn them into useful data. So that's not such a bad thing. The usual size rules that you might apply to a normal relational database where you're trying to get every ounce of performance out of it, they might not apply to Redshift, which has a totally different architecture. The format of the data on disk is highly compressed, so shaving a few bytes off of each char field is really not going to make any difference in the real world, unless you've got a really specialized use case. But what you definitely want to do is use compression, and for compression, Redshift documents that as column encoding, and that's not encoding of multi-language support or character encodings. This is specifically compression encodings. There's a lot of different encoding types that are suitable for different types of data. So if you've got a label which only has 4 or 5 values, then there's a mostly 8 compression type that will just encode every possible value to a very small integer, and then they'll actually store the integer to represent it. For example, there's run length encoding, there's standard kind of LZO encoding. The difficulty is knowing which of these to use on each column. And actually, the best approach is to let a tool figure out the best encoding by trying them all and seeing which one worked. S3 copy in Redshift can do that. Matillion table output can do that. So most of the time, it's not really worth putting any more effort in. Just hand that over to a tool to figure out for you. If we move on to the next slide, Redshift allows you to define primary keys and foreign keys, but it doesn't enforce the primary keys, and it doesn't really use the foreign keys. So why would you bother? Now, this is pretty far down the list of best practices, if I'm honest, but it is still worth doing. It's great for documentation because you are saving into the database which things you think should be unique primary keys and how you think things relate together. And the planner does use that information to know, to help it come up with a decent query plan. So it probably is worth bothering, but it's probably quite far down the list of things to worry about. So I'm going to move on to the next slide now and move on to a new topic. Once you've defined your schema and once you've got your table set up with hopefully the right distribution key and hopefully the right, you'll then want to get some data in there. Now Redshift can act like a standard database, and you can use the Redshift JDBC driver or ODBC driver. You can still treat it as a Postgres database if your tool only understands Postgres. So it's very easy for people to use these familiar tools and start inserting individual rows into the database. And you definitely don't want to do that because the amount of overhead for a single row insert, in that time you could have bulk loaded thousands of rows of data. So using copy is the way to get data in. You stage the data to some files on S3 and then use copy to bring the data in. That will apply automatic compression encodings, so it will just pick the right thing to do based on sampling the data you're loading and making intelligent choices. Now, it can sometimes make bad choices if the very first data load you ever put into an empty table is not representative of your production data. But as long as that first load is representative, it will just do the right thing, and you can just assume that it has, or maybe just double check. Copy will also load files in parallel. So if you've got lots of slices, lots of nodes in your cluster, you'll also want many files so they all have some work to do in parallel. If you have one big file, it will actually mean all the work's being done by a single compute node, and you don't want that to happen. The actual data in S3 itself can be compressed, and we would always recommend that you do that. The cost of bandwidth versus the cost of compression and decompression usually means that compressed data will actually load faster. Redshift also offers options to load over a SSH pipe, and there is still the option. It would work to use multiple inserts in SQL, and our recommendation would just be not to even try that. It's very slow, and it wasn't designed to do that really. And the last one on this slide is a suggestion to pre-sort the input data according to the sort keys. And the reason I put a question mark over that is because I'm not sure what tools you'd have available to sort those files any faster than Redshift's going to sort them anyway. I think what that's worth bearing in mind is if your data happens to be in sort key order, that's great, and it can avoid an expensive sort later on. But it's usually not worth the effort of trying to pre-sort it beforehand. And then if we move on to the next slide, a lot of people ask us how best to lay out their data in the cluster. And a lot of people go for the option of using multiple databases and even multiple clusters. We actually recommend keeping the source and the target data in a single cluster and even in a single database, and to segregate those tables using schemas instead. Schemas are logical, but they can be permissioned. So you can have a staging schema, a transformation schema, a publishing schema. You can just keep creating schemas for different sets of related tables, and then permission it so that only the right people see the data they need. And that's definitely worth doing. And the final thing to mention is there's an analyze command which gathers statistics about the way the data is distributed in the table. And that is used to make efficient query plans. If Redshift knows that 99% of a column has a single value, it will just read all that column and throw away the bits it doesn't need, much like a relational database would use an index to find just what it needed. A lot of tools do that automatically. If you're using copy, it will do an analyze as part of its work. You would have to go out of your way to turn that off. You need to be aware of what does it automatically and when you might need to do it manually. So I think I'm going to hand back to Callian now. He's got an example about loading data now.
Great, thank you very much for that, David. I'm going to share my screen now. Do let me know if you can see that. Great. So the next part, or what I'm going to show here is basically more focused on the tool. But again, we're only talking about the options that Dave's just discussed, as well as we'll see where exactly you're using these options, either within Matillion or otherwise. So right now, I've got some of these tables here, which now this is a job I use to create some of the tables. We used to demonstrate the distribution and sort key options in our previous example. So so these are basically create table components in Matillion. And the first one is for the first example, where if you notice the distribution style was set to even. And we've also set an identity column, whether it makes sense or not, along with the increment and the initial value as such. If I move on to the next component, this was from example 2, where we moved away from an even distribution and added a key-based distribution and set the key to ID, which immediately showed us performance gains when we looked into the query plan for the SQL that was generated. If I switch to the SQL tab for that component, you can also see the SQL that Matillion would generate. You can obviously look at certain aspects of it, where I was pointing out the distribution style and the distribution key that's being used. Again, moving on, the next table implemented both distribution key and the sort key. Switching to SQL, you can see these options again over here. So specifying a distribution key or a sort key as such, and these options are essentially part of your copy command, or sorry, your create table. That is, you decide on these when you're creating your tables as such. And you could be doing this either within Matillion or in a different tool or environment which you use to standardize. And of course, we've already seen how these options are helpful in making sure your queries are really performant. Now, besides these, Matillion also provides a whole load of different connectors to help you connect to various sources, pull data from them, host them in S3, and then push the data into Redshift. As an example, I'm going to use, let's say, a database query component. This is something you will use if you're trying to pull data from, say, an in-house database like SQL Server or Oracle or MySQL, or even something which is hosted on an EC2 instance or something like that. It's very typical of how you would configure a database query. So you start by specifying the connection details, like the endpoint, the username, password, and then you specify a SQL query, which will help us pull data from the database server as such. Now, when you run this component, Matillion would basically apply all the best practices that are suggested or have been discussed in previous slides, which is it'll query your data source, get data into S3, and when data is being transmitted to S3, data is going to be split into multiple files, preferably of a similar size, and the data is also compressed. So all data is then moved on to S3, at which point it'll then issue a copy command to ingest this data, and Redshift will use all available nodes to copy this data from files in S3 into the database as such. So it's effectively all of these load components that you see here, not just the database query. Any other component that's listed here would all implement the same workflow, allowing you to make best use of your of the capabilities of your Redshift cluster. Not just that, if your primary goal is to load data from S3, let's say, we have S3 load generator. It's just a tool to help you easily configure a component, the S3 load component, by simply pointing at a file. In fact, the main reason we're here is because I want to demonstrate a specific aspect. There are specific properties that I would like to discuss. So I've selected a specific CSV file from my S3 bucket. I know it's gzip compressed, so I'm going to choose that. Click on Get Sample, and Matillion basically pulled about 50 rows, as we mentioned here, and tries to come up with a suitable schema that's valid for this file that we're trying to ingest. Now, the options we're interested in, of course, you can see the various options that are relevant when Matillion is going to issue the copy command. These are, at least some of them, are about the incoming file in terms of delimiter, the encoding and stuff. As I scroll down, the ones I'm interested in is comp update and stat update. Comp update, now, in one of the previous slides, it's mentioned, we've already talked about compression encodings being applied while data is being ingested, as well as statistics being up to date by running the analyze command. So these are two properties basically help you work with compression and statistics updates as part of your copy command, that is when you're ingesting data. Now, there may be certain situations, like these are switched on by default, so depending on your data and the target table, Redshift will automatically apply any compression algorithms, as well as it'll update the statistics associated with the table. There are instances when you may prefer these to be, say, switched off as such. This would typically be in instances where the data is being loaded into a staging table, which you'll simply ingest or move into another table very quickly, and probably get rid of this table as soon as possible. So in those instances, it doesn't really, you do not really benefit from the additional processing that Redshift may perform in trying to analyze data, coming up with the best possible compression for it, or even trying to update statistics. So depending on your use case, you may choose to have them constantly on, or even switch them off, depending on your requirements. So I'm going to click on OK, and all it's going to do is generate a combination of a create table based on the metadata you've seen to the right, and a corresponding S3 load component if based on the other options that we've chosen as such. So you can see when I unticked comp update and stat update, that's now reflected here, wherein it switched both of them off. So that's all I have for at this point. It's back to you, David.
Thanks, Kalyan. So there's only really one more slide, and then we can get to some questions. So the great news is that if you've followed all the tips along so far and you've got a good schema and you're loading it efficiently, then when it comes to querying it, you've kind of done everything and it should perform pretty well. There is a little bit of housekeeping, however, that you've got to keep on top of. There's a vacuum strategy that you need to consider. So after you update or delete a row, it's really just marked for deletion. And we talked earlier about the unsorted regions as well building up as you do more and more appends. So a vacuum deals with both of those issues. It physically removes the updated and deleted rows, or rather the old versions of the updates and the deleted rows. However, there is only one vacuum allowed to be running at any one time across the entire cluster, no matter how many databases you've got on there. So you do need a strategy, and usually just vacuuming an entire database, even though it might take a while, doing it, maybe once a week or maybe overnight, it should be okay. Even if you're doing fairly frequent updates throughout the day, a single vacuum once a day should still be able to keep on top of that. Now I've got here that it's very expensive, and it is, but actually much less so now than maybe a year ago. A lot of optimizations and improvements have gone into Redshift to make vacuuming a lot less expensive. But you will notice performance start to slide if you don't keep on top of this vacuum. And the other thing that you need to keep on top of is workload management queues. Now, if you don't know what they are, it's quite a complex topic, and it's got even more complicated recently with a lot of enhancements that the Redshift team have put in. But essentially, they're about making sure queries that are more important than other queries can get a chance to run. Redshift will allow you to configure a certain number of concurrent queries, but after that, all other queries have to queue up. And the temptation to increase that number and to allow more queries to run concurrently is usually the wrong way to go. What you want is a very small number of queries running, but able to use all of the resources of the entire cluster to complete very quickly and then move on to the next query. Certainly internally within Matillion, we use a very small number of slots, but we do have a way that queries being used during ETL processing and data transformations, if a user query comes in from a front-end tool, that will definitely also get a slot. It won't sit in a queue potentially for minutes or hours waiting for a slot. Now, I think Kalyan does have some material we can quickly look at on workload management, but we also need to leave time for a few questions, so if we can make it pretty quick.
Sure. Thanks for that, David. This one's not going to take longer, so I'll just quickly talk about the workload management one. In that, so far, we've basically looked at how we can change certain settings so our queries can run faster. The next step, which is workload management, is more about certain configurations where we can ensure we're not waiting in the queue. For instance, Redshift only allows you to run certain queries at any given point in time. So there are options using workload management where you can choose how you want to prioritize between queries. So to get to it, right now I've got my Redshift dashboard page. I hope you can all see that. And you start by clicking on the parameter groups on the screen, choose your Redshift cluster, and click on Edit WLM. And here's a typical setup as such, which is right now we have about 2 queues being displayed. You have queue 1 and a default queue. You'll always have a default queue and of course the super user queue, which is not displayed here. But you can then, if you'd like to prioritize certain users, you can always add additional queues and associate that queue with a specific user group so that users in that specific group get priority. So in this case, we have 2 queues, as I mentioned, Q1 and default queue. Q1 has about 4 slots available, and Q2 has 8. And whilst this is very common, but of course you can achieve even finer control over this. So let's say, besides these 2 use, you may want further breakdown. You may set up a queue for, say, your ETL users so that you can give them highest priority. You may want to create a queue for, smaller queries as such, give them a higher priority so that they're able to be executed before any long-running queries. Or you may even want to associate a group with your analytical query user group so that you can associate more memory with those queries or more processing capabilities as such. So there are various ways in which you can do this, and I won't go on long. It's a very simple setup to engage in. You just need to understand a bit more about what else you can configure on a queue. So I'll stop at this point. I guess we don't have that much time left, so it's back to you, David.
Thanks for that, Kalyan. So I guess we're on to questions. So if you've got any new questions to add, put them in now. And
so we have, it looks like 3 questions queued up. So I figure we'll go through those, and then if we have some more time, we can answer a few others. Just to let you guys know who are on the webinar with us, if we do not get to your question, please feel free to reach out to us at matillion.com, and we can definitely get back to you on that. So we have a great question, and I'll read it out to you guys. Can you expand on using vacuum to redo the sort keys? Is it beneficial to do this from time to time? Does it lock rows? I'll let either Dave or Kalyan take that one.
Good question. Great question. So, yes, it's definitely beneficial to do it from time to time. And it doesn't lock rows. So while that vacuum's running, all normal database operations can carry on, but there will be a performance impact. So everything will be a little bit slower while that's running, but it actually doesn't block anything. The only thing it does block is other vacuums, and they just come back with an error saying, try me again later.
Fantastic. Thanks, Dave. We have another great question. What are the advantages, disadvantages using other ETL tools such as SnapLogic, Informatica? I can definitely touch on that, and Kalyan, if you'd like to maybe add a little bit of technical answer to that, that'd be great as well. Just to answer your question from a very high overview, tools such as SnapLogic, Informatica, they take a longer time to implement, and they also use more of an ETL approach as opposed to our push-down ELT. And to kind of go into more of a technical discussion about it, Kalyan, if you want to just provide a few sentences there for that question.
Sure, Rob. Yes, so I think I'll just expand on that a little bit in terms of when you talk about traditional ETL tools, in that in Matillion, we primarily, everything is based on ELT, in that all data processing is essentially pushed onto Redshift. So none of your data leaves your Redshift cluster. So when we talked about the database query component previously, you basically provide an SQL query, and then there is no interaction with the data during transit. Matillion would basically manage moving data from your source into the target, and the next time you get some control over this data is once it's in Redshift. Now, once it's in there, any transformation operation that you perform is essentially a push-down operation, in that everything's carried out on Redshift and making use of the processing capabilities that are available from the product. So that's, I think, is the typical difference between when you're using a traditional ETL tool where you're pulling the information out of Redshift before you perform any transformation, and something like Matillion, where we're simply pushing everything onto your Redshift cluster. I hope that helps.
Thank you, Callian. Seems like we have another question that just came in. If everything is run on Redshift, do we need additional expensive processing server for Matillion?
If I may just continue with my answer then, no, not really. The smallest instance size that is supported for Matillion is a T2 medium, which is about 4 gig of RAM and I think 2 virtual CPUs. It's not really that great a machine, but as I mentioned previously, everything's pushed onto Redshift, so there's not much happening on the Matillion server. So in effect, Matillion acts just like a coordinator. It doesn't do anything on its own, but it tends to effectively address any workload either to your Redshift cluster or to your source system where possible. I hope that helps.
Fantastic. Thanks, Callian. Well, it seems like that's all the time that we have. On behalf of myself, David, Callian, and the whole team here at Matillion, we want to really thank you for joining our webinar. And like I mentioned before, if you have any follow-up questions, please feel free to reach out to us at matillion.com, and we'll get back to you with an answer. So again, thank you so much. Have a great day, and we look forward to hearing from you. Take care.